Welcome back. This is section 1.2, exponents and radicals. So in this section, we're going to look at the definition of an exponent, some properties of those exponents, and then also what happens if we have fractional exponents. All right, so to start us off here, integer exponents. So if a is some real number and n is a positive integer, then the nth power of a is a times itself that many times. And so in this case, we're multiplying a times itself n times. Okay, so the n tells you how many times to multiply that base by itself. And so again, a is called the base, and then the n value here would be the exponent. All right, so if we want to simplify this first one here, we've got 1/2 to the 5th power. Now, if you have a calculator, obviously you could put 1/2 to the 5th power in there. I'm going to actually write this all the way out so we can see what's actually happening. So we're multiplying the base 1/2 times itself 5 times. So that's 1/2 times 1/2 times 1/2 times 1/2 times 1/2. Okay, now when we multiply fractions, remember we can multiply their numerators together and multiply their denominators together. So if I do that here, 1 times 1 times 1 times 1 times 1, 5 of those is still going to leave us with 1 in the numerator. And then if we do 2 times itself 5 times, that should give us 32. And so 1/2 to the 5th power should be equal to 1/32. All right, now if we look at the second one here, we've got -3 raised to the 4th power. Now notice the negative is in parentheses here, meaning that it's part of the number that we're raising to the 4th power. So when I do this multiplication, this is -3 times itself 4 times. Now, if we do that, 3 times 3 times 3 times 3, if we do that 4 times, that's going to give us 81. Now, notice here, because we have an even number of negatives, those negatives are actually going to cancel each other out and turn into a positive. And so this overall answer now is going to become positive 81. Okay, so in general, if you raise a negative to an even power, it should turn positive. If you raise a negative to an odd power, an odd number of negatives will actually come out negative. All right, now this last one, the difference between this and the second one is the negative itself is not being grouped with the 3, so it's not being raised to the 4th power. Only the 3 is. So this is really like saying negative, and then in parentheses, 3 times 3 times 3 times 3. So only the 3 gets multiplied by itself 4 times, and then the negative stays out front. If I do that now, 3 times 3 times 3 times 3 is 81 still, but because of the negative out front, the overall answer here is going to be -81. So just be careful there. If there is no grouping around the negative sign, the negative itself is not being raised to that power. Therefore, we just have to keep the negative outside. All right, now 0 and negative exponents. So as long as a is not 0, the base itself is not 0, and it's a real number, then n is a positive integer. In those cases, a to the 0 is always equal to 1. Okay, so any real number to the 0 power always equal to 1. And then a to the negative n, we can rewrite that as a fraction 1 over a to the positive n. So anytime you have a negative exponent, we can actually just move that down to the denominator and make it a positive exponent instead. All right, so if we take a look at this one now, 4/7 to the 0 power. Well, 4 over 7 is a real number, and we just said that any real number to the 0 power is equal to 1. So this right here is just going to be 1. All right, now the next one, we have a negative exponent. We have x to the -1 power. Remember, we said to turn that into a positive exponent, we can just put it in the denominator. So we're going to have 1 over x to the +1. And then x to the 1st power is really just x, so we don't really need the exponent anymore, so we can just call that 1 over x. Okay, and then this last one here, we have -2 raised to the -3 power. So the first thing I'm going to do is I'm going to get rid of that negative exponent by moving this whole thing to the denominator. So that's going to turn into 1 over -2 to the +3 power. Now we can raise -2 to the third power. Remember, that means -2 times itself 3 times. Well, when I do that, that should give us a -8. So this is 1 over -8. Okay. Or you could just write that as -1/8. So again, because the negative's in parentheses here, the negative gets raised to the third power. Raising a negative to an odd power, though, is going to keep it negative, and then 2 times 2 times 2 will give us 8. All right, now some laws of exponents. So if we're multiplying two bases that are the same, and we have exponents on both of those values, when we multiply, we're actually going to add the exponents together. So again, as long as the bases, the a values are the same, and we have exponents, when we multiply, we add exponents. Number 2 here says that if we have the same base, again, both bases are a, and we have exponents on both of those values, when we divide, we actually subtract the exponents. And then the third one here, if we're raising a power to a power, so we've got a to the m, and then that whole thing is being raised to some other exponent n, then we're actually going to multiply those exponents together. And so we're just going to get a to the m times n. And then our fourth law here says that if we have the product of two real numbers, a and b, in parentheses being raised to some exponent, we can actually just do a to the exponent and b to the exponent and then just multiply those things together. And the same thing is true for division. If we have a divided by b in parentheses raised to the n power, that's going to give us a to the n over b to the n. All right, and then our sixth property here says that if we have a over b to the negative n, so we have a negative exponent now, we can actually take the reciprocal of the fraction on the inside and turn that into a positive exponent. So it becomes b over a, and then the exponent is going to become a positive. And then our last law here, if we have a to the negative n and b to the negative m, okay, so in this case we have two different exponents, both of them happen to be negative, we can move the negative to the numerator to make it a positive, we can move the numerator to the denominator to make it a positive exponent, and we end up with b to the positive m over a to the positive n. All right, so let's see if we can apply some of those laws here. So we've got x to the fourth times x to the seventh. So our bases are the same, they're both x's. We're multiplying, which means we're going to add the exponents together. So this is going to turn into x to the 4 plus 7, and then 4 plus 7 is going to give us 11, so we get x to the 11th power. Again, whenever you're multiplying, as long as the bases are the same, we can add the exponents. Now the second one here, similar thing, we've got y to the fourth times y to the negative 7. Again, we're multiplying, bases are the same. So this is going to become y to the 4 plus negative 7. Same thing as 4 minus 7, which is going to give us a negative 3. So this just becomes y to the negative 3. Now, in general, we typically don't leave negative exponents. And so remember, we have that property that told us if we have a negative exponent, we can rewrite it as a positive by moving it to the denominator. So this is 1 over y to the third power. All right, now the next one here, we're doing some division. Bases are still the same. We have a c as the base. So remember we said we can subtract exponents when we're doing division. So this becomes c to the 9 minus 5. 9 minus 5 is 4. So now we have c to the fourth. All right, and then our next one, we have b to the fourth, and that entire quantity is being raised to the fifth. If you raise a power to a power, we're going to multiply those exponents. So this becomes b to the 4 times 5. 4 times 5 is 20. So we end up with b to the 20th. All right, now the next one, we actually have two parts. We have a 3 and an x being multiplied together, and all of that's being raised to the third power. So remember, if you have two values inside being multiplied and being raised to an exponent, we can basically distribute that exponent to each of those pieces now. So this becomes 3 to the third times x to the third. And in this case, we can actually simplify 3 to the third because that's just 3 times 3 times 3. It's going to give us 27x to the third power. And then this last one, again, with division being raised to a power like this, we can actually distribute that 5 to both of the terms there. So that's going to give us x to the fifth over 2 to the fifth. That becomes x to the fifth over, and then 2 to the fifth power, 2 times 2 times 2 times 2 times 2 is 32. So we get 32 in our denominator. All right, so now we've got some multiplication and some powers all happening in the same problem. So we got to think about order of operations, how we're going to simplify this thing. So remember, your first step with order of operations is going to be parentheses. Okay, so we look inside of our parentheses here. We don't have anything that we can actually do. Okay, so there's no like terms, nothing that can be combined, nothing that can be simplified. So then we're going to go to the E, which stands for exponents. Well, I do have this exponent on the outside of my set of parentheses, the second set, so I'm going to go ahead and distribute that in to take care of that exponent. So I'm going to keep the first set, 2a to the third b squared. This now becomes 3 to the third a to the third, and then b to the 4 times 3. Because remember, when you raise a power to a power, you're actually multiplying. And in this case, really, this exponent on the a is an understood 1, so we're really doing 1 times 3 there. That's how we get a to the third power. And I'm going to go ahead and simplify everything we have there before we try to multiply this out. So again, I'm going to keep 2a to the third b squared. 3 to the third is 27. We have our a to the third, and then we multiply 4 times 3. That's going to give us b to the 12th. All right, now at this point, we only have multiplication left. So now I'm going to do my multiplication. We can actually multiply the 2 and the 27 together. So 2 times 27, that should be 54. Now we have an a to the third and an a to the third. And remember, when we multiply, we're going to add those exponents. So when we add 3 plus 3, that's going to give us 6. So we get a to the 6th power. And then again, we have our b's here. We're multiplying those together. That means we're going to add their exponents. 2 plus 12 should be 14. So we get b to the 14th. At that point, there's nothing else that can be simplified, nothing that can be combined, no negative exponents to deal with. So that right there would be our final answer. All right, now the second one here, again, we want to go through order of operations. If you look inside the parentheses here, again, there's nothing that can be simplified up front. Okay, so then we're going to go to exponents. I can distribute the 3 to the first set of parentheses and do the same thing with the 4 to the second set. So that's going to give us x to the third over y to the third times, and again, when I distribute this now, I'm going to multiply these exponents because I'm raising a power to a power. So we get y to the 8th, x to the 4th over z to the 4th. All right, now at that point, we can just multiply these two fractions together. And so remember, to do that, we're just going to multiply straight across the numerator, straight across the denominator. Up top, then, we have an x cubed and an x to the 4th. I'm going to add those exponents because those bases are the same, and that's going to give us x to the 7th. Now we have the y to the 8th. That doesn't combine with anything else, so my numerator just keeps y to the 8th. Now in the denominator, we have a y to the 3rd, a z to the 4th. Those are not the same. We can't combine them, so that stays y to the 3rd, z to the 4th. Now that we've got it as a single fraction, we always want to look and see, is there anything else we can do to simplify this? Well, I actually have a y in the numerator and denominator here, so I can use that property that says I can subtract exponents when I'm dividing. So my x to the 7th stays up top. Y to the 8th over y to the 3rd, I subtract those exponents, I get y to the 5th, so that goes up top as y to the 5th. and then the z to the fourth is going to stay in the denominator. Now, my rule for doing these when you have division like this, I go ahead and always start with the top value, subtract the bottom value. If it comes out positive, I'm going to keep it in the numerator. If for some reason I subtract and I get a negative exponent value, then I know I can put it in the denominator to make it a positive value. Okay, so always do top minus bottom, and then if you end up with negatives, move those to the denominator. As long as it stays positive in the exponent, just keep it up top. And again, at that point, there's nothing else that can be simplified, so there's our answer. All right, so now we want to eliminate negative exponents and simplify each one of these expressions. So it's kind of up to you whether you want to move the negatives first to turn them into positives. You can also just do the division with the negative exponents and simplify that way. You will get the same answer regardless. Okay, so I think some people prefer moving them first just to get rid of the negatives and then working with positive values. If we do that, we have 6s, and now this s to the negative 2, I'm actually going to move it to the numerator, and so that becomes times s to the positive 2. I have the 2 in the denominator. We have the t squared that was there. And then we have this t to the negative 4 that I'm going to move to the denominator now and make it t to the positive 4. Now we can simplify. Well, 6 over 2 is actually just 3, right? So that fraction simplifies to 3 over 1. So I'm going to have a 3 in my numerator. S times s squared, we're adding the exponents. Remember, this is an understood 1 right here now. So that's going to give us s to the third power. And then the 2 is already simplified. So then we just have t squared times t to the fourth. Again, if we add those exponents, that should give us t to the sixth power. And at that point, there's nothing to simplify. That is our answer. Now, again, if you wanted to do the subtraction up front using the negative values, you will get the same answer. Again, 6 divided by 2 is 3. If we do this now, we have s to the first over s to the negative 2. Well, when we subtract that, that's 1 minus negative 2. That turns into addition now, and 1 plus 2 is 3. And so we actually end up with s to the third power when we do that subtraction. And now I can do the same thing with my t's. We have t to the negative 4. I'm subtracting 2 from that, so negative 4 minus 2 is going to give us negative 6. So we have t to the negative 6. And all that's over 1 for right now. But now, because I have that negative exponent, I know I can move that to the denominator to make it a positive. It's going to give us 3s to the third over t to the sixth. Again, the same answer we got doing it the other way. So again, it doesn't matter if you move the exponents first to make them positive or just do the subtraction using the negative values. You should end up with the same answer regardless. All right, now the next one, remember we have a property that says if we have a fraction and we have a negative exponent, we can actually take the reciprocal of that fraction and turn that into a positive exponent. So the reciprocal here is going to be 3z to the third over y. And now my exponent becomes a positive 2 instead. Now at that point, we can actually just distribute that 2. So that's going to give us 3 squared times z. 3 times 2 is 6. And then we have y squared. And then the only other thing we could do there is 3 squared we can simplify. So 3 squared is 9. So we're going to end up with 9z to the sixth over y squared. Now, again, you could have technically distributed the negative 2 to all of your terms. Then all of your exponents are negative, though, so they'd all have to move to become positive, and you'd still end up with exactly the same answer there. All right, now radicals. Okay, so the square root of a equals b means that if we square the b value, it should be equal to a. And in this case, b has to be greater than or equal to 0, because when you take the square root of any value, it should come out positive or 0. You're never going to get a negative answer there. Now, nth roots. So if n is a positive integer, the principal nth root of a is defined as follows. So the nth root of a is equal to b, means that b to the n power is equal to a. So again, with square roots, that just means that b squared is equal to a. Now this is saying, well, no matter what that index is, so this value right here is what we call an index, no matter what that number is, if I take b and raise it to that power, it should be equal to a, which is the value inside the radical. Okay, so if n is even, then we must have a greater than or equal to 0 and b greater than or equal to 0. So you have to have a positive value inside and a positive result. If n is odd, you could actually end up with negative values for both a and b. Okay, so we can take like a cube root of a negative value and get a negative value as the answer. But if the index is even, both of those values have to be positive. All right, now the properties of our roots. So if you have the nth root of a times b, we can split that radical in two and say that's the nth root of a times the nth root of b. So multiplication, we are allowed to split up into two separate radicals. Same thing with division. If we have the nth root of a divided by b, we can take the nth root of the numerator divided by the nth root of the denominator. Now, if you have a root of a root, what we can actually do there is combine those two into a single radical, and we can multiply the index values together. So notice here we have the nth root of the nth root of a. We're just multiplying m times n to give us our new index. All right, and then these last two are very similar. It's just one works for odd values, the other works for even. So the nth root of a to the n is just going to give us a as long as the n is an odd value. The nth root of a to the n is equal to the absolute value of a if n happens to be even, because remember before we said the a and b values both need to be positive in that case. And so you would have to take the absolute value of a here just to ensure that we have a positive value if you're taking an even root. Okay, but again, odd roots can be negative. That's why we don't need the absolute value bars for number 4. All right, so now we want to take the cubed root of x to the 4th power. Now, to do that, what I'm going to do first is I'm going to break down that x to the 4th power to a point that I can actually take a cube root. Okay, so you don't have to do this work every single time, but I'm going to try to explain what's happening the best I can here. So remember, x to the 4th means x times x times x times x. So I'm going to rewrite this that way. Now, because we're taking a cubed root, I'm looking for groups of 3 x's being multiplied together. So what I notice here is I've got one group of 3 with 1 x left over. That means that I can rewrite this thing as the cubed root of x to the 3rd times x. So again, because my index was 3, that's why I look for a group of 3. Now, the cubed root of x to the 3rd, according to our properties, because we're allowed to split this up now, this becomes the cubed root of x to the 3rd times the cubed root of x. And as long as that index matches the exponent on the inside, we know that this should just be equal to x now. And we cannot take the cube root of x because its exponent is smaller than the index. Okay, so we end up with x times the cube root of x, and that is our simplified answer now. All right, now let's take a look at this next one. So we're taking the 4th root of 81 times x to the 8th times y to the 4th. What I'm going to do this time is I'm going to go ahead and split up all of these terms, because remember, we're allowed to do that as long as there's multiplication there. So this just becomes the fourth root of 81 times the fourth root of x to the eighth times the fourth root of y to the fourth. All right, now the fourth root of 81, and we can actually do this in our calculator. If you first put in the index that you want here, so in this case, this will be a 4, then you're going to go to your math menu. And in that very first one, you should have an x root key on there. And so by putting in the 4 first and then selecting that, you're telling your calculator you want to take the fourth root. And then in this case, you would type in the number you want to take the fourth root of. This is 81. And when you do that, that should give you 3. Okay. And again, that's because 3 times itself 4 times should give us 81. Now, the next one, the fourth root of x to the eighth. So we could split this up just like we did the first one and say that's an x times itself 8 times. Well, if we do that, we have the fourth root of x times x times x times x, x times x times x times x. And remember, we're looking for groups of 4 this time because we're taking a fourth root. So I've got a group of 4 here, and I've got a group of 4 right here. So now, really, this is the fourth root of x to the fourth times the fourth root of x to the fourth. Well, the fourth root of x to the fourth, that should give us an x. Same thing with the other fourth root of x to the fourth. So we have x times x now. And when we multiply like bases, we add their exponents. We have x to the first times x to the first. Adding those together should give us x to the second, or x squared. And so now this just becomes x squared. Now, a shortcut for this is if we can actually divide the exponent by the index, we can do that. So in this case, 8 divided by 4 is 2, and that's how we get x to the second power. So whenever you can actually divide the exponent and the index, that's the shortcut. And then you don't have to do all this work over to the side where you're breaking it down. All right, and then the last piece of this one, we have a fourth root of y to the fourth. Again, that should just give us a y. Now with this one, we have to be careful because it is an even index. Okay, so on the first one with an odd index, we didn't have to worry about it. But remember, one of those properties said that if we take an even index here, we have to remember that this is an absolute value. Now, the reason we don't need the absolute value on the previous part of this one, when we took the fourth root of x to the eighth, we end up with x squared. Any value squared is going to be positive or 0 anyway, so we don't really need the absolute value bars around that one. If you put them there, it's fine. It's not wrong, but we don't really need them since x squared should come out positive regardless. All right, so now combining radicals. So we've got the square root of 32 plus the square root of 200. Now, to combine radicals, you have to have the same index, and you have to have the same value inside your radical. Well, right now I've got a square root of 32 and a square root of 200. They're both square roots, but the numbers inside are not the same, so I can't add them the way they are right now. So I'm going to try to simplify first, and then we'll see if we can combine them from there. So what we're going to look for are perfect squares that are factors of these values inside the radical. Okay, and when I say perfect squares, I'm thinking about these values. 1 squared equals 1, therefore 1 is a perfect square. 2 squared is equal to 4. 4 is a perfect square. 3 squared is 9, so 9 is a perfect square. 16 is a perfect square. 25 would be the next one. 36, 49, 64, 81, 100, 121, and 144. And if you know all the way up to 12 squared, I think those are the ones you probably need to kind of know from memory. Anything beyond that, you could probably just use a calculator. Okay, but if you can at least remember the ones from 1 squared through 12 squared, those are the perfect squares you need to know. Okay, so again, now we're going to ask ourselves, do any of those values go evenly into 32? Well, I'm looking right here and I see, well, 16 actually goes into 32 2 times. So I'm going to rewrite this as 16 times 2. So again, I'm looking for perfect squares that are factors of the value inside the square root. Okay. Now I'm going to come over here to the square root of 200. Again, I'm looking down my list. I've got a few options here, but you always want to try to find the largest value if possible. And 100 would be the largest value that is a factor of 200. So I can rewrite this as the square root of 100 times 2. Now, remember, we're allowed to split up these square roots as long as there's multiplication inside. So I can take the square root of 16 and the square root of 2 separately. Well, the square root of 16 should give us 4 because 4 squared gives us 16. So now I know this is going to turn into 4 times the square root of 2. And then if we look at the square root of 100, square root of 100 should give us 10 because 10 times 10 is 100. So that's 10 times the square root of 2. Once I've done that, now we have two square roots that both have a 2 inside. These are now like terms, and I can actually add them together. So when we add them together, it's kind of like adding together like terms with variables. I'm going to add together the coefficients, the numbers on the outside, and I'm going to keep the square root of 2 piece since that's what they have in common. So 4 plus 10 is 14, and then we have the square root of 2. And that would be our final answer in this case. So again, we can't add them together the way they start, but once we simplify them and we get 2 square roots of 2 there, we can then actually add those two terms together because now they're like terms. All right, so now we want to do the same thing with this next one. We do have variables this time, so that's the key difference. So we're going to take the square root of 25 times the square root of b. That's the first step. Well, the square root of 25 should give us 5. So this first piece is going to become 5 times the square root of b. Now, b to the third power, we need a group of 2 so that we can take the square root. So this I'm going to rewrite as the square root of b squared times b. Because b squared times b to the first, we would add those exponents. That would give us the b to the third that we started with. Now again, I can take the square root of each of those pieces individually. The square root of b squared should give us b. So this is 5 times the square root of b minus b times the square root of b. Now, honestly, at that point, you could just leave your answer like that. Everything is simplified. These are technically like terms now because they both have a square root of b. But when we write this, it's really just 5 minus b times the square root of b, okay, which is not a lot prettier than what we had in the previous step anyway. So again, if you want to stop right here, that's fine. But if you do want to combine them, you would combine the 5 minus b part, and then you would keep the square root of b since they're like terms. All right, and then this last one here, we've got the square root of 49x squared plus 49. Now, a common mistake on a problem like this is you go, oh, they're both 49s. I can take the square root of both of those values, and then you try to separate this. But remember, we're not allowed to separate addition. We can only separate multiplication or division under a radical. So the only thing I can really do with this one right now is see if there are any factors that could come out that I could then take the square root of. Well, both of these terms have a common factor of 49. So I'm going to rewrite this as the square root of 49 times x squared plus 1. Okay, so basically I'm just taking the 49 out of each of the terms. If I take 49 out of the first term, that leaves me with x squared. If I take a 49 out of the second term, 49 divided by 49 is 1, so I still need that plus 1 there. Now we have multiplication. Okay, so we have the square root of 49 times x squared plus 1. Well, I can take the square root of 49 then, and that's going to give us 7, so that's going to come to the outside. But I'm still left with the square root of x squared plus 1. And again, it's extremely tempting to say, oh, I can take the square root of x squared, I can take the square root of 1, so let's just do that. Again, there's addition in between them. We're not allowed to separate that, so this is as far as you can actually go with this one. This would be our final simplified answer because we can't separate that addition under the square root. All right, now rational exponents. So for any rational exponent, m over n, where m and n are integers, okay, and n in this case has to be a positive value, we're going to define a to the m over n as the nth root of a raised to the m power, or you could also write it as the nth root of a to the m, where the nth power is inside the radical. Okay, so both of those things are equivalent. It doesn't matter which way you write it, so long as the n becomes the index and the m becomes the exponent. And then it tells us down here, if n happens to be even, then we're required that a has to be greater than or equal to 0. Okay, so again, if your index becomes an even value, we have to have a positive value inside. All right, so let's see if we can rewrite some of these now and then simplify them. So we've got 4 to the 1/2 power. So again, using what we just saw on the previous slide, I know this is going to become some kind of radical with a 4 on the inside. Okay, so my base always goes inside. Now I'm looking at my fraction. The numerator of that fraction is going to become the exponent. And the denominator of that fraction is going to become the index. So now we have a 2 as our index, we have a 1 as our exponent, so we're taking the square root of 4. Well, the square root of 4 can actually be simplified now, and so that should just give us 2. So again, anytime you have a fractional exponent, we can rewrite it as a radical. Just make sure the denominator becomes your index, the numerator becomes your exponent, and then if you can simplify that further, then we want to do that. So let's take a look at the next one. So again, I know it's going to turn into a radical because we have a fractional exponent. I know the 8 is going to go inside. In this case, the 3 is the denominator. That's going to become our index. So I'm going to put my 3 out here. And then the 2 is the numerator. That's going to become the exponent. So I'm going to put my 2 right here. Now we're going to simplify. Okay, so if I simplify here, I'm going to go ahead and square the 8. It's going to give us the cube root of 64. And now again, if you want to use your calculator, you can do that nth root thing that we showed in the calculator earlier, but the cube root of 64 here should give us 4. Now, remember we said it doesn't matter whether you put that exponent on the inside or the outside. So let's say we had written this one the other way instead, and this became the cube root of 8, all raised to the second power instead. Well, in this case, we would want to take the cube root of 8 first. Well, the cube root of 8 is actually just 2. But then we have to raise 2 to the second power, and 2 squared is equal to 4. Same answer. So it does not matter whether you do the exponent on the inside of the radical or on the outside of the radical. It should still simplify to the same value no matter what. All right, and then this third one here, first thing I notice is we have a negative exponent. So that's always going to be the first thing I want to get rid of if possible. So I'm going to move that to the denominator and make it a positive. So now we have 1 over 125 to the 1/3 power. Now we can rewrite that 1/3 power as a radical. So this now turns into 1 over The 3 becomes my index. 125 goes on the inside, and it's just being raised to the first power because that's the numerator of my fraction. So again, we're just taking the cube root of 125 now. We can use the calculator for that if you don't know what that is already. Cube root of 125 is 5, so we end up with 1 over 5. All right, so now we've got some where we have fractional exponents, but then we also have some other operations going on. Okay, so let's think about how we can simplify these. We've got a to the 1/3 times a to the 7/3. The bases are the same. We're multiplying, which means we're going to add the exponents together. So that's the first step. When I do that, we already have a common denominator of 3, so I can just add the numerators. So this should become a to the 8/3. Now, that answer is perfectly acceptable because there's nothing else that we can really do with that. If you wanted to rewrite it as a radical, you could do that. And so just remember this would be the cube root now because there's your denominator, and then a to the 8th power. And you could even simplify that if you wanted to. Look for groups of 3 here. So this will be the same thing as the cube root of a to the 6th times a squared. Cube root of a to the 6th. Remember, our shortcut is we can divide those values. 6 divided by 3 is 2, so we get an a squared. And then we have our cube root of a squared, because in this case, I cannot take the cube root of a squared since the 2 is smaller than the 3. But again, a to the 8/3, perfectly acceptable. But if you wanted to rewrite it as a radical, then just make sure you always simplify as far as you can. All right, now the next one, same thing. I've got some operations I can do first, and then we'll see what that looks like. So first thing I notice is I've got multiplication in the numerator. I'm going to multiply those, which means I'm going to add the exponents. It's going to be a to the 9/5 over a to the 3/5. And at that point, we still have division. We have common bases, so I can subtract the exponents. So that's going to leave us with a to the 6/5. Again, if you wanted to rewrite that as a radical, you could, but in this case, you can just stop with a to the 6/5. All right, now the next one here, we have this exponent on the outside. Remember, we can distribute that to each of the pieces on the inside then. So this is going to turn into 2 to the 3/2. A to the 9/2, and then B to the 12/2, which is the same thing as 6. Okay, so you get 12 over 2, so that's just B to the 6th. Now, the only thing I would probably really worry about here is that 2 to the 3/2. So I'm going to come out here and do that work to the side. That's the same thing as the square root of 2 to the 3rd. And since we're taking a square root, we're looking for groups of 2 here. So this is the same thing as 2 squared times 2 to the 1st. Square root of 2 squared is going to give us 2. And then we have to keep the square root of 2 now. So now overall, this becomes 2 square root of 2, a to the 9/2, b to the 6th. So again, the a to the 9/2, perfectly acceptable to leave it like that. With the 2 to the 3/2, because we can actually simplify that, it's a numerical value, that one I would probably go ahead and switch to a radical and simplify. All right, and then this last one down here, first thing I notice is we have this exponent on the outside. There's nothing to simplify inside the parentheses, right? So I always look for that first. But now I can go to my exponents. So this is going to be 2 to the 3rd multiply here when you raise a power to a power, so that's x to the 9 over 4. Then we're going to multiply 1/3 times 3. That becomes y to the first power. Now we're multiplying by y to the 4th over x to the negative 1/2. Now, again, it's up to you whether you want to go ahead and move the x to the negative 1/2 up and make it a positive. I'll go ahead and do that. So now we have x to the positive 1/2 up here. I'm going to put a 1 in the denominator just to hold that place. And now it's just a matter of simplifying all of this. Well, 2 to the 3rd should give us 8. Sorry, I'm going to have to write it over to the left so I have room. Then we're going to have y to the 4th over y to the 1st. And remember, when we divide, we subtract exponents, so that's going to give us y to the 3rd. And now we have this x to the 9/4 times x to the 1/2. I need to add those together, which means I need a common denominator. So 9/4 plus 1/2. Same thing as 9/4 plus 2/4. And that's going to give us 11 over 4. So we end up with x to the 11 over 4. Nothing left in the denominator except a 1, so we don't really need it. And so this right here would be the answer to that one. And if you want to put the x term before the y term, you could do that, right? The order there really doesn't matter, though, because multiplication is commutative, so it doesn't really matter what order those variables go in. All right, so again, we want to simplify each one of these now, and we're going to do that by rewriting these as fractional exponents. So we have 1 over the cube root of x to the 4th power. So first step, let's rewrite this radical here. I'm going to keep the x. We know the exponent becomes the numerator, the index becomes the denominator, so that's going to be 4 over 3. And now, if we wanted to, we could actually rewrite that as a negative exponent, right? Since we're actually just trying to write this as rational exponents. So this turns into x to the negative 4/3. Now, in general, we're not going to leave answers like that, but it is good to know how to rewrite things like this in their fractional exponent form, because there will be times, especially if you do take calculus, where you'll want to be able to write it in that form just to make it easier to work with. All right, now the next one here, we've got 2 square root of x times 3 times the cube root of x. Now, we can't multiply a square root times a cube root. So what we're going to want to do first is convert these into fractional exponents and then see if we can work with them at that point. So this first one here, we're going to have 2x. Remember, this is an understood 1 here, and this is a square root, so there's an understood 2 as your index. So this becomes 1/2. And we're multiplying that by 3x. And again, there's an understood 1 as your exponent. The index is 3, so that becomes 1/3. Now, at that point, we can multiply the 2 and the 3 together. So 2 times 3 is 6. And because we're multiplying like bases, we can actually add their exponents. So we're adding 1/2 plus 1/3. But to do that, we need a common denominator. Common denominator would be 6 here. So this is 3 over 6 plus 2 over 6. And that's going to give us 5 over 6. So now we end up with x to the 5/6. So again, in their radical form, we're not allowed to combine a square root and a cube root, but once we convert them into fractional exponents, now we can add those exponents together when we multiply, and so we can actually simplify this. And then this last one here, we have a square root of a square root, and remember, one of our properties said that when you have that, we can actually just multiply those indices together. That's going to give us the 4th root of x. Now, the other way to think about this would be to think of it in terms of fractional exponents. So really what we have here is x to the 1/2. There's your square root on the inside. And then we have this other square root around the whole thing. So the whole thing is being raised to the 1/2. And remember, when we raise a power to a power, that's going to be multiplication. So 1/2 times 1/2 is 1/4. And then when we rewrite that, that becomes the 4th root of x. Okay, so again, applying the property that we looked at before, where you just multiply the index, you can do that, or you can convert these into fractional exponents and work with them that way. All right, and then finally, rationalizing the denominator. So it's often useful to eliminate radicals in a denominator, and to do that, we're going to multiply the numerator and denominator by some expression. Okay, so it's going to vary depending on what the original fraction was. Okay, we're going to multiply by something to try to eliminate the radical that's in the denominator. Okay, now a fractional expression whose denominator contains no radicals is said to be in standard form. Okay, so we're doing this to get it into standard form. There are times where you might want to rationalize numerators also, okay, but for the most part, we do rationalize denominators. All right, so let's take a look at these. We've got 2 divided by the square root of 3, and we want to rationalize that denominator, meaning we want to get rid of the radical that's in the denominator. So the way we're going to do that is we're going to multiply numerator and denominator by the same thing. Okay, because that's the same thing as multiplying by 1. That's completely legal. Well, the thing we're going to want to multiply by is the square root of 3. So since I have a square root of 3 in my denominator, if I multiply top and bottom by square root of 3 now, this is going to give us 2 square root of 3 over, and then the square root of 3 times the square root of 3, you could think of that as the square root of 9, because they're both square roots. I can combine them. 3 times 3 is 9. But we know the square root of 9 is going to give us 3. So this just becomes 2 square root of 3 over 3. And now that fraction is rationalized because there is no radical in the denominator. All right, now the next one here, we have 1 over the cube root of 5. Well, if we follow the same logic we just used, I would multiply top and bottom by the cube root of 5. Now, if I only do that, that's going to give us a cube root of 25, which is not going to simplify. So because it's a cubed root, I actually need to multiply by another cube root of 5. So basically, depending on what that index is, that's going to tell you how many times you need to multiply. Because we have a cubed root this time, we need 3 of those factors so that we can actually simplify that denominator now. Well, if I multiply all this now, 1 times the cube root of 5 times the cube root of 5, it's going to give us the cube root of 25 over, and now we have the cube root of 5 times the cube root of 5 times the cube root of 5. That's the same thing as the cube root of 125, but the cube root of 125 is just 5. So now we get the cube root of 25 over 5. And I no longer have a radical in my denominator. Now it's rationalized. All right, now this last one, we have the 7th root of 1 over a squared. Now, just remember, I could rewrite this as the 7th root of 1 over the 7th root of a squared, because division, we are allowed to separate like that. 7th root of 1 now is just 1, right? So that we can actually simplify pretty easily. So now it's just a question of what do we need to multiply the denominator by to get rid of the radical that's down there? Well, remember with the cube root of 5, we had to multiply by the cube root of 5 and the cube root of 5 to end up with 3 total cube roots there. Well, similarly, we have the 7th root of a squared here. I need to make sure I have 7 a's so that I can actually take the 7th root. Now for this one, that doesn't mean that I have to multiply by 6 more seventh roots of a squared. I can just look at this and say, well, I've got an a squared. That's 2 a's being multiplied together. I need 7, so I need 5 more. So I'm going to multiply this by the 7th root of a to the 5th. And again, whatever you do to the bottom, you have to do the same thing to the top. Okay, so now when I do that, remember we just said the 7th root of 1 is just 1. So the numerator now is just the 7th root of a to the 5th. And now when we multiply down here, a squared times a to the 5th, if we add those exponents, gives us a to the 7th. So we have the 7th root of a to the 7th. But the 7th root of a to the 7th is just a. So now we have the 7th root of a to the 5th over a. Now, that's not to say that you couldn't have multiplied by the 7th root of a squared 6 more times. It's still going to simplify to the same answer if you do that. But we don't have to do all that work as long as you recognize that we need 7 a's. We already have 2, so we just need 5 more in this case. All right, so that's all we've got for 1.2. As always, if you have any questions, please let me know, and I will see you next time.